All right, friends and neighbors, time now for another networking video in this series on spanning tree, rapid spanning tree, and VLANs. Before we get started, hey, we're trying to see how well we're doing here, so go ahead and subscribe and like if you're helped out by the videos. So this one is going to be, what is this 802.1q you speak of? Well, let's go back in time again, but we don't have to go quite as far back. 802.1q, or at least rapid spanning tree portion of 802.1q, got its start as 802.1w, the rapid reconfiguration of spanning tree. And the whole point was to make up for some of the problems that we saw in 802.1d spanning tree. And the biggest one is probably that it was slow. So the nice thing about spanning tree is that it was plug and play, meaning that all of the switches did it. And if the vendors agreed on how they were going to do it, which they should because it was a standard, then you could just stick a switch in the topology and it would automatically configure itself along the lines of spanning tree and everybody would do it the same. But as we said, it was really, really slow. The other thing is that while you can do some tweaks on spanning tree, to do major improvements, you had to do an overhaul. Now, the changes that were seen in 802.1w were good enough that in the updated version of 802.1d 2004 says this: STP has now been superseded by rapid spanning tree. So anything that you saw after that time that had anything to do with spanning tree is probably going to be rapid spanning tree, at least in terms of the standards. And then, of course, clause 17 in that same standard describes what rapid spanning tree is and how it works and all of that stuff. The other funny thing is that this is about the only place that you ever see the language of bridge used. Everybody else says switching. Now, 802.1q, virtual bridge local area networks, that particular standard there were really a couple of big differences. One is obviously the use of rapid spanning tree, but really 802.1q is about virtual local area networks, or VLANs. So in a VLAN, you want to make sure that you have all of the same capabilities, right? You want to have priority and expedited traffic capability. Now we're going to see where that is right inside a trunk frame. You can actually see the priority field right there. Grouping. Hey, can anybody say IGMP? So the generic Attribute Registration Protocol, or GARP, goes along with IGMP and PIM and all of those things to handle not only multicasting, but also grouping of nodes together. Obviously, virtual local area networking services. There's a change to the forwarding process, and really what we're talking about there is the inclusion of the VLAN ID in the source address table and the divvying up of where the traffic is actually supposed to go. So really, it's designed to be support for all things virtual local area network. And 802.1q 2003 just simply says, yeah, we're doing rapid spanning tree. But there's also a clause in 802.1q that specifies the use of something called multiple spanning tree. We'll talk about that a little later on. So rapid spanning tree, what are some of the big differences? Well, first of all, maybe we'll say that a lot of it is the same. The timers, the BPDUs, in many ways are the same, at least as far as the comparison algorithm is. We're still going to find a root switch. We're still going to eliminate loops. We're still going to have the same exact comparison algorithm being used. But the big deal is that in rapid spanning tree, we changed the use of some of the fields. So we'll talk about it here in a minute, but the flags field especially. So rapid spanning tree, as the name might indicate, is faster. It's much faster in recovering to the redundant links. So it eliminates loops really quick, the same way that common spanning tree does. 802.1d spanning tree went bam when it found a loop, same thing. But finding alternate pathways or redundant pathways, well, that's where spanning tree fell down, and rapid spanning tree is much, much faster. Some additional messaging, or at least flags in the messaging, and then some state and role changes are also there. So here is the change to the states. We know that all ports come up blocking. Well, rapid spanning tree calls that discard. And then eventually we transition to listening and then learning and then forwarding. Well, we're just going to go from discard to learning and then forwarding. The other important change was that the blocking port role. So in spanning tree, 802.1d spanning tree, a blocking port is just that, it's blocked. But in rapid spanning tree and in the Cisco improvements that we saw, a block port can either be an alternate or a backup port, and we'll describe the differences in a little bit. The designated root and designated and root are variables of the port, or what we call the state of the port. So their place in the universe is the same. Root ports still receive BPDUs, designated ports still send BPDUs, but we'll see here that we indicate that state by the flags. So let's do a sample topology here. We've got a couple of switches connected in a loop, and the thing that I'll point out is that we have the root in the lower left, and I want to take a look at that port 16 on the upper switch. Okay, so that's sort of where we're paying attention. So we take a look at that top switch, and we know that port 1 and 5 were looped together. So one of them was automatically blocked, and that gave us the backup because, and I'll do these again here in a little bit, but it's backup because there's no other path back to the root. It doesn't hear about another path back to the root. Its only path to the root is through port 1. So that's why it's blocked and backup. Here we see that we have root and designated as forwarding ports. Now 16 though is blocked, but it's an alternate because even though it has a pathway back to the root, that blocked port is an alternate path back to the root, so that becomes important. Everything else is pretty much the same on this particular screen for rapid spanning tree. As far as the ports go, remember that we talked about portfast in one of the other videos, and portfast was a way of identifying that a port was connected to a host, and so it didn't need to be a point-to-point link. When you do rapid spanning tree, those ports are now identified as edge ports, and they go forwarding much more quickly. Remember that 802.1d spanning tree doesn't really make use of the ports very much, so really had a couple of flags for the ports, and that was it. We just identified that we had a topology change going on, and that was pretty much it. But here we're going to make use of the flags field to indicate states of a particular port or what's going on at a particular point in the topology. So we've got 6 bits that are going to be used here, and I'll actually explode them out here a little bit, but we'll see the state and the role identified. We will see that whether or not we've got a proposal going on or an acknowledgement of proposal, and that's really where we're trying to establish the election of the root switch. And then we've got some versioning differences, things like that, which should be pretty clear because we actually have changed the version of the protocol. Here is an RSTP BPDU. If we start all the way from the top, we see that the protocol version identifier is actually rapid spanning tree. And then what I've done here is I've expanded out the flags field. Normally in the traditional way, we would see very little use of the flags field, but here we've got forwarding yes, learning yes. We've got a designation for the port role, and a no for topology change and no for proposal. If there was a new root elected or if there was a change in the topology, we would see those flags being changed. Below that, the root ID, the root path cost, the transmit bridge ID, and the root ID are all the same. The timers are all the same. But that's the real big difference that you see in the BPDUs. Well, one of the differences here is that in traditional spanning tree, it's very common to see the root send out a BPDU and then it sort of flows away from the root. So other BPDUs are generated upon receiving a root BPDU. In this case, what we're seeing is that switches send their info every hello time, even if they haven't heard from the root. Now, there might be a topology change coming, but they still send out their information. Now, in this way, when the hellos are sort of forced, if you haven't heard from a neighbor, you know that there's a problem. And so the magic speed increase here is that traditional spanning tree, 802.1d spanning tree, said, I'm going to wait for the max age timer to expire, which was 20 seconds. Here, 3 hello times go by, which is just 2 seconds apiece. Then I'm going to take action on the situation. This provides for much failure link detection no matter where it is. That's the whole requirement of the hello time. And if the root fails, it's also recovery from a loss of root much more quickly. Now, I mentioned this earlier. The edge ports are defined. This is the portfast implementation. The uplinkfast implementation is the alternate route back to the path. So both of those, see, it's really clear where those are implemented. In the case where we are an edge port, you're not going to generate any of the BPDU stuff. But if you hear a BPDU, you instantly transition from an edge port to a non-edge port or a point-to-point port. So when we start a rapid spanning tree topology, Initially, what we're going to do is the exact same thing that we've always done, which is try to elect a root switch. And that's where the proposal is. So what's interesting is that you see every switch, assuming it's the root. And if there is nobody else out there, then nothing really happens. But if there's a switch that thinks it has a superior BPDU, then a proposal will be generated, and that'll be the flags, and then you'll see that go, and they'll go back and forth until they finally elect the root switch. When we see topology changes, all non-edge designated ports are blocked, and the reason for this, or at least in the discard state, is that you don't want to start forwarding into a loop, right? We don't want to create that problem. Once we have the negotiation phase is over, we've figured out the topology, then we're going to start moving things to forwarding. The priorities that we saw in the root ID, the transmit bridge ID, and then the port ID, different priorities, but all those priorities, they work in the exact same way. Here is an example of two packets. The red arrow at the top is showing you that there are two MAC addresses there. So these are neighboring switches on point-to-point links, and they're exchanging BPDUs. And you can see that they're going back and forth. This is unusual because when a root is elected, BPDUs flow in one direction. Once the topology is stabilized, you just see BPDUs flowing in one direction until there's a topology change or a new root might be out there, in which case that starts the proposal phase, and in this case the proposal flag is set, and that's part of the messaging here. Here are some topology diagrams that show where alternate and backup ports might be. In the case of the diagram on the left, the root port is, or the root bridge is the one on the top, and we can see that we need to block a port. But that blocked port has a secondary pathway back to the root, and so this becomes a blocked and alternate pathway. The one on the right is quite a bit different. There's only one pathway back to the root. So even though we're blocking a particular port, now that the reason that one's blocked is because the downstream device is not actually a switch, it is a hub in this case. And so the switch has to block itself, but this becomes a blocked and backup port because there is no other way back to the root. There's still the only one way, so it doesn't become an alternate. Here we're just looking back at the same output that we had before, and now we have a better understanding of why we see down there in the bottom, the root and designated ports, right? Our forwarding ports still are going to be root or designated, but here we see why one might be blocked and backup and why the other one is blocked and alternate. Well, once we have a topology change, the behavior is much in the same way. It's just supposed to be faster with rapid spanning tree. Somebody generates a topology change, right? They set the topology change flag, so we have a TCN, and we start the TC timer. Now, one important detail for spanning tree and rapid spanning tree is that when you have a topology change, the SATs are flushed. We wipe all those out. And the reason for that is that you don't want traffic being forwarded in multiple directions. You have no idea which is the best way to forward traffic, particularly in the case when you have a topology change, when the topology is actually in flux. But worse would be if you actually have a loop. So we flush the source address table so we don't know where to find nodes. What we're going to do is relearn where the node locations are or how they can be reached once the topology is stabilized. Until the timer expires, you're going to keep sending BPDUs with that topology change flag set. That's in the flags field. There's no need to wait for the root to be informed, or if the topology change is somewhere else in the network that doesn't involve the root, right? All of this action can take place without updating the root, which is why everybody's required to do the BPDUs, whether they hear one from the root or not. So this way, we get rid of old information, we relearn where the locations are, we fix problems with the topology, and we move on. Now, multiple spanning tree. Okay, so we know that if we connected a whole bunch of switches together and we created loops, switches in that one VLAN would resolve into a single spanning tree topology. If you add VLANs, by default, all the VLANs would resolve their topologies in the exact same way. Let me say that again. It doesn't matter how many VLANs you have. They're going to have the same topology that the single VLAN topology had. And that is because you're just adding the VLAN onto the priorities. And so they'll all resolve along the lines of really the MAC addresses. And so the root would be the same for all of the VLANs. Now you can manipulate that, and we'll see that later on in another video, but that's not what we're talking about here. Multiple spanning tree, which is part of 802.1q, allows the formulation of regions. Now it's a little weird. It's actually quite confusing, because if I said I wanted to have multiple VLANs but one spanning tree instance, we can wrap our head around that. I can even wrap my head around saying I want a different topology for every VLAN, so the number of VLANs would equal the number of spanning tree instances. Multiple spanning tree says, well, we're just going to create a couple of regions, and then we'll figure out how we want all of our VLANs to interconnect and how we want to forward traffic. So the behavior of multiple spanning tree is just like RSTP, except that each region has a root all its own. And each region is comprised of switches that have the same MST IDs. So the language in the standard, because I gotta admit, it's a little confusing. You don't see this used very often. The MST BPDUs are exactly the same as the BPDU format for RSTP and for STP. Now remember that RSTP modified the fields, but the BPDU is largely the same. MST does the same thing. It just modifies the available fields there. The idea is that you want to be able to set up the regions but still be compatible with switches that are not doing MST. So the border of the region is going to be compatible with whatever else is out there. And you want the regions to be able to talk to each other as well. But it's a complex addition. You have to sort of wrap your head around it. The standard has some diagrams that are really straightforward and some of them that are just painful to try and understand because they've got so much symbology and everything else. But here is an example of the MST diagram right out of the standard. And it's confusing enough, or it's complex enough, that they've included statements like this. The specification of MSTP is such that the nominal replacement of an entire MST region by a single RSTP bridge leads to little change in the behavior of the remaining of the bridge local area network. So you could replace an entire region with a single switch. But what you're trying to do is trying to set up forwarding regions that control the way traffic is forwarded for a particular set of networks or VLANs. The design is intended to assist those familiar with STP and RSTP specifications to comprehend and verify MSTP and to administer bridge local area networks using the MSTP specification. All right, so you can see that on the diagram anyway, and this is really all that I want to cover here. The little vertices there, the A, B, C, D, and so on, those are actually networked. So there's IP-based nodes in there and VLANs. So think about forwarding between VLANs and how that would work. And the VLANs would be associated with an MTP region. Now the idea certainly makes sense, but you really have to think about how you're going to forward traffic. Well, thanks very much for watching. Thanks for listening. Hey, like and subscribe if I helped. That's our look at RSTP and MST. Maybe next time we'll take a look at how rapid spanning tree and VLANs interoperate. Oh, and may your packets always reach their destinations.